Hello, today we discuss the increasing and decreasing of a function. Let's say, suppose y equals to fx is a function defined on a domain D. So x belongs to D. So what is my D? Suppose D equals to AB. So AB belongs to real number. AB are real number. So this is my number line. So minus infinity to infinity. Here is A and here is B. So actually y is defined in this interval. Okay. Now the definition of increasing and decreasing. Let's see. So 1. Suppose x1 less than x2. Okay. This implies fx1 less than fx2. Okay. So when x1 less than x2 implies fx1 less than fx2, this condition represents the increasingness of the function y equals to fx. Okay. So what? Suppose the graph is this, and suppose this is my x1. So for x1 and this is my x2. Okay. So for x1, what is my fx1? This is fx1. What is x2? This is x2, and for which what is my fx2? So this is my fx2. Some point. Okay. So this is my fx2. Now as a length, which is greater? fx1 is this only, and fx2 is actually in this length. So which is greater? fx2 is greater. So this is actually our condition, x1 less than x2. fx1 is less than fx2, that is fx2 is greater than fx1. So in this case we get the situation of increasingness. Okay, this is very simple. Let's see. Number 2. When x1 less than x2 implies fx1 greater than fx2. Mind that x1 less than x2 implies fx1 greater than fx2. In this situation, we have the result fx or y equals to fx is decreasing function. Let's see. Suppose the graph is this. Okay. So here is x1 and this is x2. Okay. Now for x1, suppose this is x1, this is x2. So what is my fx1? This is fx1. Okay, and this is my fx2. Actually here is x equals to 0. This is a negative real axis and this is a positive real axis. Okay, so x1 is less than x2. In this case fx1 as a length this and fx2 as a length this. Which is greater? fx1 is greater. So this is actually our condition. So this condition represents the decreasingness of the given function y equals to fx. That is actually when x1 less than x2 implies fx1 less than fx2. That is actually some similarities of the sign, less than sign. Okay, and number 2 is x1 less than x2 is same, but fx1 is greater than fx2. That is less than sign is changed to some greater. So x1 and x2. In this situation we get 2 is represents decreasingness and 1 is represents increasingness. This is our basic definition. So in basic definition we solve some problem. So take a problem. Let y equals to x square. So this is a simple card. Suppose is range minus 2 to 2. Okay, then we take any 2 point in this interval where actually the function is defined. So the function is defined in this interval, and actually in this interval is a subset of the real number line. Real number line, this is actually the set R. Okay, so y equals to x square. So what is the graph of y equals to x square? This. But at x equals to 0, after this x equals to 0, when x greater than 0, like as this curve, and this is increasingness. When x less than 0, this curve actually decreasingness, and x equals to 0, the point is the most important. Let's see, we discussed it. But in this basic definition, all type of problem solving is not so easy. So there is a theorem, theorem 1 and theorem 2. These two theorems are important to us to solving such type of problem very easily, but interesting. Okay, let's see. Theorem 1 is, first of all, for any function, suppose y equals to fx, this, so f is differentiable. Okay, differentiable, suppose at a point at x equals to c, so c is a real number, then f dashed c greater than 0. So f dash represents the first derivative of the given function y equals to fx. Okay, so f dash x equals to actually ddx of y. So y equals to fx actually first derivative. So f dash c at a point c is greater than 0 implies f is increasing at a point x equals to c. Okay, now theorem 2, f is differentiable at, suppose x equals to d, then f dash d less than 0. So this gives the result f is decreasing at x equals to d. Okay, so this condition is mandatory in both cases. F is differentiable. Okay, so left hand derivative and right hand derivative are same. It is very simple. So in this situation, we only check the condition f dash c. So first derivative of the function fx. So which is greater than 0 and or less than 0. So sign is greater than or less than. So if greater than 0, so represents the increasingness of the function fx. If less than 0, so decreasingness of the function fx at a point d, and increasingness at a point c where f is differentiable. Okay, on the basis of two theorems, we solve any such type of problem, any such type of function having increasingness and decreasingness as a property. Okay, so let's see. As a familiar example, y equals to x square. Okay, x belongs to minus 2 to 2. Okay, so first of all we check the condition like as this. So first derivative is needed to here. So y dashed. So this equals to 2x. So derivative with respect to x first time, or first derivative y dash equals to 2x. Okay. Now the point is most important, where y dash x is equals to 0. That is y dash vanishes. That is first derivative vanishes at a point. May or may not be 1 point, it may be more point. Okay, let's see. So let's see, y dash equals to 0 implies 2x equals to 0 implies x equals to 0. So x equals to 0 is a point. The term critical point. The term is critical point, where the first derivative of the given function vanishes. Okay. So what is the graph of y equals to x square? This x equals to 0 is a point. This is my x is greater than 0. This is my x is less than 0. Okay, this is very simple. Now, according to our theorems 1 and 2, so f dash c either greater than 0 or less than 0. Only these two situations we only conclude the increasingness or decreasingness. Okay, so when y dash is greater than 0, that is 2x is greater than 0, but 2 is also greater than 0, that is x is greater than 0. So x is greater than 0, so y dash is greater than 0 actually. So then y dash is also greater than 0. In this situation f is increasing. This is increasing sign. Okay, so look at this. When x is greater than 0, x is greater than 0, in this case, suppose here x1, suppose here x2, fx1 and fx2, which is greater? fx2 is greater, because x1 is here and x2 is this. So fx2 is bigger as length of x1, fx1. Okay. So this is actually increasingness, definition of increasingness, which we also discussed from first and the basic definition. Okay, let's see. When y dash is less than 0, y dash is less than 0, that is 2x is less than 0, that is x is less than 0. So when x is less than 0, 2 into x also less than 0, that is y dash is less than 0. So y dash less than 0. So y dash less than 0 represents the decreasingness from theorem 2. This. Okay. So this is a decreasingness. You may take any point from negative real axis. You should get y dash negative. So from theorem 2, we actually get f is decreasing at x equals to d, but here every negative real number represents also satisfies this condition. So this is true for every negative real number. So this is the decreasingness of the function y equals to x square. Okay. So we'll also discuss more example like this. Let's see. This example is completely based on the theorem 1 and 2, which are help to solve such type of problem very easily and interestingly. Let's see. Suppose y equals to x to the power 5 minus 5x to the power 4 plus 5x cube minus 1. Okay, x belongs to real number. Okay, so for first derivative y dash equals to 5x to the power 4 minus 20x cube plus 15x square. Okay, so for simplicity we have to take common. X is 5x square, so x square minus 4x plus 3. Okay, so 5x square, x minus 1, x minus 3. Okay, for simplicity, y dash can be written as factorized form. This is x minus 1 into x minus 3 into 5x square. Okay, so find out the critical points of the function y dashed. Why? Actually, why? So where y dashed vanishes. Let's see. Where y dash vanishes? When x square vanishes, that is actually x equals to 0. So critical point, set of critical point, x equals to 0. X minus 1 can be vanished for x equals to 1. So 1 is also critical point of y, where y dash is vanishes. Also 3. So this is the set of critical points, a set of critical points. Here more than one critical points. Okay, so let's see. So we now divide the line. Suppose here is x equals to 0, here is x equals to 1, here is x equals to 3. Sure, let's see. Suppose we take x greater than 3, that is in this portion. Okay, so when is x greater than 3, look at this, y dashed. When is x greater than 3, that is actually x minus 3 is positive, because more than 3 number minus 3 actually positive, and it is also positive because more than 3 number minus 1 is also positive, and 5 into x square, this is the x square term, that is square term is always positive. So actually total positive into positive into positive, so this is positive. So y dashed greater than 0. So for greater than x greater than 3, y dashed is positive. So this represents from theorem 1. This represents the increasingness of the given function y equals to fx. This is okay. Let's see. So y is increasing for x greater than 3. Okay. So this is actually not equals to, is strictly greater than 3. Okay. Add x equals to 3, y dash vanishes, that is y dash vanishes. This is the critical point. So critical point. Critical points of f. Okay. So for x greater than 3, y dash greater than 0, and this implies y is increasing for x greater than 3. This is very simple. Let's see. This is number 1. Number 2, 1 less than x less than 3. In this interval, we observe it when x is less than 3. When x is less than 3, that is this term x minus 3 is actually negative number. X minus 3, when x is greater than 1, so more greater than 1 minus 1, so actually this is positive and this is also positive. So positive into negative. So this represents y dashed, sign of y dashed less than 0. This is very simple. So this represents y is decreasing. Where? For 1 less than x less than 3. Okay. Next, number 3. When x is less than 1 and greater than 0. Okay. When x is less than 1 and greater than 0, look at this. When x is less than 1, so less than 1 term, here suppose you put a less than 1 term, minus 3. So this actually totally negative now. And this is also negative, less than one number minus 1. So this is also negative. So negative into negative, this actually positive. And x square term is always positive. Okay. Then we decide the y dash is again greater than 0. Y dash is again greater than 0 implies y is increasing for 0 less than x less than 3. Okay. Okay. Let's. Number 4. When x is less than 0. This is our last portion. So x less than 0 means this. So here y dashed. What is the sign of y dashed here? So look at this. When x is less than 0, x square term is always positive. So x is less than 0, that is this term is negative and this term is also negative because some negative number minus 1. So this also negative and this is a negative number minus 3, this also negative. So together forms y dash represents the negative sign. So y dash, this negative and this negative. So together form positive. So y dash is again greater than 0. So implies y is increasing. Okay, for increasing for x less than 0. So in this portion y is increasing. In this portion y is also increasing. So is the sign 1 less than x less than 3, that is in this portion y is decreasing. So this is a decreasing sign. And lastly, when x is greater than 3, that is in this section y is again increasing. So for division of this interval, let's see, x equals to 0, x equals to 1, x equals to 3, these 3 points are the critical points. These points are important to us to finding when you derive the function y as a y dashed. So when y dashed is 0, that is y dash vanishes at which point? Here x equals to 0, 1 and 3. In this point y dashed when vanishes, so these points represents the critical points, and actually the critical point measure the increasingness and decreasingness for this portion. So these portions are divided by these critical points. Okay. So function of critical point are divided the interval of this, where increasing, where decreasing. At a critical point, function is neither increasing nor decreasing.
24.
Okay. Let's. So we now discuss more example. One more example. Let's see. So this is more familiar to us. Okay.
24 কত?
Suppose y equals to sin x. Sin x is very familiar to us. So suppose we want to check the increasingness and decreasingness on the interval. So simplicity we have to take. So 0 to pi. Okay. So graph is very easy. Let's see. So this is your x equals to 0. This is your x equals to pi. So this is pi by 2. Okay. So this is my y equals to sin x. Sure. So when y equals to sin x and we want to check increasingness and decreasingness in the interval 0 to pi, what should I do? So first of all, according to our theorem, we want to the derivative of the function. So y dash equals to cos x. Okay. Now y dash equals to cos x, but when y dash vanishes, that is cos x vanishes in this interval. Let's see. So graph of cos x. We also draw the graph. So suppose here x equals to 0, here x equals to pi by 2, here x equals to pi. This actually x equals to pi is this point. So 0, pi by 2, pi. From 0 to pi, only this point y dash is 0. So what is the point? Implies x equals to only pi by 2. Also cos x vanishes at the point. This is our 3 pi by 2. But 3 pi by 2 does not belongs to this interval. So this is not actually our interest. Okay. So here critical point is only x equals to pi by 2. So in this critical point, we want to check when x is greater than pi by 2 and x is less than pi by 2. Sure? So when x is greater than pi by 2, look at this. What is the sign of y dashed? So what is the sign of y dashed? Let's see. Y dashed is actually cos x, and cos x when greater than pi by 2. Cos x, y equals to cos x. This is the graph of cos x. Okay, this. So when x is greater than pi by 2, that is in this portion. Here y dashed, what is the sign of y dashed? Actually here y dashed is this. Here y dashed is this. Here y dashed is this. Okay. So this is the sign of y dashed. So this is actually negative. This is a real number line, and this is actually negative number. So this is y dash is less than 0. Okay. So less than 0 implies y is decreasing from our theorem 2. Recall it from the theorem 2. We observe when sign of first derivative less than 0, so function is decreasing. Now, when x is less than pi by 2, when x is less than pi by 2, that is x is less than pi by 2, here fx is actually this. Actually, x is less than pi by 2 is y dashed. So cos x, this is the cos x graph, is actually positive. So here y dashed is greater than 0. Y dashed is greater than 0 implies y is increasing from our theorem 1. Recall it. From theorem 1 we also discussed. So y dashed is positive implies y is increasing function in this interval. This. So observe it in our y equals to sin x. So when x is greater than pi by 2, when x is greater than pi by 2 means in this portion. Okay, in this portion y is increasing. What is my y? Y equal to sin x. Sin x is decreasing. This is the decreasing sign. Okay, and this is the increasing sign. So greater than pi by 2, the function is decreasing. So you observe the decreasingness, the definition of decreasing from first. Okay, and when x is less than pi by 2, less than pi by 2 means in this portion. In this portion, y is increasing because you also get, suppose this is your x1 and this is your x2. x1 is less than x2. fx1 is less than fx2 because this is your fx1, this is your fx2 as a length. So this represents actually increasingness of the definition from first. So from 0 to pi, the sin x, y equals to sin x, the function y equals to sin x increasing for 0 to pi by 2 and decreasing for pi by 2 to pi. Okay, so actually this less than, x is less than pi by 2, but the interval starting from 0, so minimum position of x, it may be less than 0. Okay, but here x is greater than pi by 2, but the interval is 0 to pi, so actually maximum point is pi. So this is the actual discussion about increasingness and decreasingness. Okay, So these are totally completely based on your exam. So very simple. Theorem 1 and theorem 2 gives us all such type of results. You can solve very easily such type of problem. Okay. So thank you very much.